Thank you to the NSRC for letting us present today. And what we want to do is talk about the impact of energy when we look at CO2 systems in a warm environment. And with that, didn't move back to where it was. There we go. Let's look at refrigeration system in general, because, we understand that a refrigerant, whether being a natural or the current synthetics that we use today, are used as a medium to remove heat. We want to remove heat from where we don't want it in our display cases or walk-in coolers and freezers. We bring it back up through the system and up to the condenser gas cooler where we eject that heat into the ambient condition. So when we look at that heat transfer, we take our liquid line and take liquid into our evaporators. We remove that heat by absorbing it, bringing it back through our suction lines as a vapor. We go through the compression cycle, get that to go up to the gas cooler where we eject that heat as we had stated, getting us the efficiency of bringing back a liquid refrigerant, and that's how the system works. Now, when we talk about efficiency in a refrigeration system, there are a lot of components that we look at across the industry of how we improve refrigeration efficiency. Looking at the display cases, electronic expansion valves, how do we do different things with the coil surfaces? How do we control superheat control? Improving that efficiency. Then when we come back to the compression system, what type of compressors are we using? What type of unloaders? How are we taking the efficiency of the compressors in mind with either digital, variable speed, or VFDs within the compression side? And then also when we get up to the condenser gas cooler, what type of fans are we using to move and displace that heat out of the refrigerant back into the atmosphere? Do we need to do water? All of those things impact efficiency of the overall system. But what we want to do is look at CO2, and we use a pH diagram for that. And then, of course, we can get into the complex part of it. Is it hot outside? Is it cold outside? Is it cloudy? Is it windy? Is it raining? Is it snowing? All those things have an impact on the environment. But we're going to say, wait a minute, let's stop. Let's slow down and take a moment and think about it. Why does ambient have an impact on refrigerant? So we're going to look at that same pH diagram, okay? And when we look at that, we know that pressure is equal to temperature and that enthalpy is equal to energy. So as we move up and down this scale, we're affecting temperature. And as we move left or right, we're use of energy. So when we look at that, the refrigerant cycle, we go from a liquid, we absorb heat, go to a vapor. When we get rid of the heat, we go back to the liquid, okay? Evaporation, absorbing heat, using energy to do that. And then we use energy to condense it, bringing it back. That's a refrigeration cycle, no matter what type of refrigerant you're using. So when we start looking at a traditional system, we look here, again, left to right is energy, bottom to top is pressure. We have a pressure drop at the expansion valve. We use energy to absorb that heat across the evaporator. We have case fans and your discharge air. We use an increase of pressure at the compressors. And then we go back up to the roof and we use energy to get rid of that heat back to a liquid. That's the refrigeration cycle. It will be no different when we look at CO2. But when we look at CO2, the one difference is the critical point of CO2 is at 87 degrees. So what we want to do is understand how that operates based on the ambient temperature and what is that impact on energy. So when we look at running below the critical point, that is when we're in the subcritical region and it's usually cooler outside. The temperature is down. So we have that heat transfer available at the gas cooler to get the heat out of the system. So when we look at a booster system running in a subcritical operation, we run very efficient. Again, energy is left to right. We run at a little bit higher pressure, which is the top to bottom. Now, when we get into the ambient condition and it exceeds that critical point, that's called the supercritical region, okay? That's when it's warmer outside or it's hotter and we're having a harder time to get that temperature differential to get the heat out of the refrigerant system. So the system runs left to right, just a little bit different, and then we exceed that critical point where there is no temperature differential and we end up returning and we cannot get the heat out of the refrigerant and we return as a vapor and a liquid. So what's that mean within a refrigeration system? We understand that there's a subcritical and a supercritical operation, okay? We want to run more subcritical and less supercritical, but the word transcritical, just to help clarify it, is that the system will transition between a supercritical and a subcritical operation, and that is based on the ambient. That ambient does base on how we get the heat out of the system and how it impacts energy. So we understand that part of it, we go back to the refrigeration cycle. And again, we want to get the heat out of the cases and get it out to the gas cooler. Okay, what impacts CO2 is the ambient. And what is that temperature differential? What is it that we need to do to get the heat out of the system? And the more heat we get out of the system, the more the system runs. So again, refrigeration cycle doesn't change. We just have a little bit more of an impact with the ambient condition. So when we understand that, we have to look at how that operates. Okay, on a cool day, we're going to look at the return from the gas cooler and how we go through the high pressure control valve into the flash tank. So when it's cool outside and we're in that subcritical state that we talked about, we're going to come back with a solid column of liquid coming back from the gas cooler because the ambient allows us to get all the heat out. And then we have liquid refrigerant available to do what we need to do in our liquid lines. Okay. What changes a little bit when it gets warm outside is that we're not getting that temperature differential up at the gas cooler. So therefore, that's why it's a gas cooler. It's going to come back as that vapor and liquid. As that vapor builds up in the flash tank, we use it and go through the bypass valve. Now with the bypass valve, we take that vapor and reprocess it back into the medium temp suction. And anytime we do something a second time, we're not getting any gain in the efficiency of the system. We're just using more energy to accomplish that. So understanding that, we're still going to have that liquid refrigerant needed to do the refrigeration in the store, no matter what the ambient temperature is outside. We're just going to do it a little bit inefficiently. So we have to look at what can we look at for technologies to improve the efficiency of the refrigeration system. We can look at adiabatic gas coolers, the use of water. We can also look at parallel compression. There are ejectors, a couple of different kinds. There's a low pressure ejector as well as a high pressure ejector. And then also some developing technology we're looking at with the pressure exchanger. So let's first take a look at the gas coolers. Two types of gas coolers. We have the air-cooled gas cooler and we have adiabatic, where again we use the pads. So looking at an air cooler and we look at the extreme dry bulb condition, if you're under 100 degrees or 101 degrees as shown, we're allowed to use, or we have an option to use air-cooled. Now, keeping in mind that the air-cooled in a cool climate works very well because we have the temperature differential. In a warmer climate, air-cooled will still work. Most of the time it'll be subcritical, but we'll have to have some difference in energy usage when we're in that supercritical state that we talked about, which is why we often look at 101 degrees or above, we look at adiabatic. And what adiabatic will do is allow us to operate in warmer climates. So when we talk about warmer climates and how this works, ASHRAE has 3,000 or so points around North America. When we look at those, less than 14% would actually require adiabatic. So the decision needs to go based on your location, based on the capacity or size of your rack. What is the right application for me? Can I do air-cooled? Can I do adiabatic? Can I do air-cooled with another technology to improve the efficiency of the system, but still maintain what we need to do for refrigeration in a warmer climate? So when we look at adiabatic, the advantage of adiabatic is when it is cool outside and we're running subcritical, we can use the adiabatic dry. Then as the temperature outside warms up, we then wet the adiabatic pads, allowing us to pre-cool that air coming across those pads to about 2 degrees off a wet bulb. Therefore, the air going across the condensing coil is actually cooler than the ambient air. So we have that temperature differential that we talked about so that we can get the heat out of the system in a warmer climate. So keep it in mind too, that there are certain set points that you have to understand the application of when you need to be in water saving mode or when you need to be in energy saving modes. So having that right set point strategy also assists in improving that performance. So let's take a look at parallel compression. As I mentioned, if we don't have parallel compression, we use the medium temp suction group through the gas bypass valve to reprocess that gas. But what parallel compression allows us to do is we take that gas as it builds in the flash tank and we put it back up to a heat exchanger because we want to make sure there is no liquid in that and it's just vapor going to the compressor. And then we operate a parallel compressor inside of the medium temp suction group that runs at actually a separate saturated suction temperature, allowing us to process that gas more efficiently. Again, we're just taking the vapor and processing it more efficiently. Then we have an option of doing pressure exchangers. And as I mentioned, low pressure ejectors. And as we talked about that, there are kind of two types. One is the low pressure ejector, which allows us to take that higher pressure coming back from the gas cooler and then mixing it with a lower pressure and using that lift from the medium temp suction group, giving us the ability to process that gas more efficiently so that we can run in a better, warmer condition more efficiently. So when we look at that, then we look at the high pressure. Oh, there we go. The high pressure ejector does the same thing, but it runs in conjunction with parallel compression. Again, using that medium temp suction to help improve the return gas, and then using the vapor that's left in the system back up to that parallel compression. So the question would be, well, how do I know whether I want to do a low pressure ejector or a high pressure ejector? And again, that would be based on where you are in your capacity. So what we would look at is say a low pressure ejector has a sweet spot, if we want to call it that, when you're running in a warm climate that is under 450,000 BTUs. A high pressure ejector along with parallel compression would work when we have larger racks, larger size systems. So when we look at that, there is a difference between how we would want to apply it, what's the energy saving potential versus the cost benefit. So we look at that too. So there's also the pressure exchanger. Now, this is another thing that we're in a pilot stage right now, verifying the application and the energy savings, but it just helps us improve that energy that we need to use between the high pressure and low pressure side of the system. So it helps us process that heat more efficiently. And we're deploying that and looking at that as an option as well. So when we really look at what does that mean to me, how do I understand where is the best way for me to use the right technology or the right application when we look at CO2 in a warmer climate? And part of that would be as if you're in a cool climate with a low load, you can do air cool, adiabatic, low pressure ejectors. Remembering that each application will vary based on your amping condition, the size of your system, and then what makes sense for your energy rate, your efficiency rate, and then how do you look at things in an ROI. But we know as the temperature increases from cool to warm to even a hot climate, we need to change the way we look at things. And maybe that's adiabatic or a low pressure ejector. And as we mentioned, as the capacities increase, that also changes your business decision on what is the right application. Then do we look at air cooled? It opens up the door for parallel compression or high pressure ejector with parallel compression. Or do you look at a pressure exchanger? And then when you get into that larger rack system as well as the hotter weather, maybe it's a combination. Maybe it's adiabatic, high pressure ejector. How do we look at the right technology and how do we apply that based on our location, our operation, and our ambient condition?
Hey, Robert, it looks like you have your hand raised. Do you have a question? You just go back to look at another slide.
Sorry.
If you have a question, Robert, you just need to write it into the chat, or write it into the Q&A, and then we can ask that. If you just accidentally hit the hand raise, then that's something else.
Yeah, if you actually hit the hand raise, we're going to say hi back. But put the question in and we certainly answer in the question and answering part.
So I had a question.
Okay.
Actually, as you're going through.
Okay.
When we first kind of started this out, my knowing CO2 and what I know of CO2 about warmer climates and kind of where we fall, like sort of south of that Mason-Dixon line, right, where things, because I live in the south, but I'm from the north.
Right.
So I kind of know both climates in that area. And at first I thought, okay, we definitely need to get to a point to where we can get that change of state. Right? My refrigeration background takes me right to, we're coming out of the gas cooler, coming out of the condenser, if you will, and we're trying to get to that change of states. But then also we have the flash tank that helps us out with that and the drop in pressure. But when we can't get that change of state, we don't just have the one option of the adiabatic where, right, we drop 2 degrees above dew point, I think you said, which is like can be a 12, 15 degree temperature drop, of air going across once it hits that coil, giving us that additional heat rejection. So in that though, you mentioned parallel compression. We can use the gas cooler up to 100 degrees, 101 degrees, which most people think it's 87, can't go any hotter, which takes out a large portion of the states, which is not true. So it goes up to 101. Then after that, we look at adiabatic, parallel compression with ejectors high and parallel compression with ejectors low, and then the new technology that we're looking at. So that's 5
different options,
6 combinations of options. And looking at this slide, you've done this for decades and you know your stuff better than anybody, but how do you walk through that with a customer? Where do you take them first?
Well, again, I think the whole myth of CO2 is that equator line, the Mason-Dixon line.
Right.
It's not, yes, it gets hotter below it, gets cooler above it. It doesn't mean you can't do CO2 below it. It just means you have to handle it differently. You have to look at a different strategy based on the capacity and your conditions and your ambience. Now, what I would say there is, and the reason why you'll see that I didn't go through the traditional charts of if you do New York and Texas and Miami and California, here's your savings based on your all over the place, because it really varies based on your benchmark. What is your baseline when we're setting a comparison and a comparison? How does energy come into play? Energy is only part of it based on your utility rate, your return on investment.
Sure.
Okay,
Yep.
so we have to look at the bigger picture. So all this is getting you to understand is that there are different things to look at when we take CO2, put it in a warm climate. It's not that you can't do it. It's that you need to look at it differently. And there are technologies, there are processes that you can do to look at this. There are utilities that provide incentives. So maybe you want to do one versus the other based on what they will subsidize. But the bottom line is CO2 will work in any climate.
Yep.
It's just that you have to treat it a little differently. And there are technologies out there that make it worth doing CO2 in any environment. Just handle it and understand it, and then figure out what's best for you. You have to look at the size of the store. You have to look at the ambient temperatures. You have to look at, how and where do you apply that right technology? And you have retailers that have different size stores in different states, and they may have 2 different strategies based on that. Or you may have one store owner that has 100 stores in one state, and they'll apply to that particular condition. So the bottom line is that you have to be able to do your homework, understand how energy is used within your store environment, and then how do I maximize the potential in any technology to meet that ability to do CO2 in any climate.
And when we look at those, I've seen some charts, you've shown them and had them in other presentations. When we look at these charts, we know, because we've done the homework, we've done the test sites, we've done the engineering papers on this, as to seeing what the percentage is. Because if you have a baseline of, I get this percentage of savings or efficiency with this technology,
right,
you can actually show the differences of cost savings versus percentage where you have this combination of technologies, or this technology all by itself versus this other technology all by itself.
Correct.
We actually have that information.
Yeah, and the other thing too is, and I started this when you look at how we look at energy within a system. So you could have an HFC system, HFO system, traditional, with air-cooled condensers, with no energy efficient fan motors, with a mechanical valve, and just regular on-off compressors.
Yep,
okay, and then you say, okay, this is how we look and use it as a baseline, and then all of a sudden you go to adiabatic, you go to variable speed motors, you go to unloading on your refrigeration system.
Yep.
All those things in itself make that system more efficient. Okay, so when you look at numbers and comparing things from apples to apples, that's what you have to start as a baseline. And where we go with how do we transition to CO2, how do we adopt it, how do we make it viable so that I can be cost effective long term. Energy is one part of that, and then you have to do that based on your particular needs and then work with your provider to look at it, the right comparison, and apply that right technology that makes the sense for you.
Let's say you're starting to have a conversation.
Mhm.
So some of our students out here, those that are watching out there, they're just getting ready to start having that conversation. They're wanting to help their customer switch over, get away from HFC, move over to natural refrigerants, and they're looking at the system as a whole. Are they going to baseline the system that they've had if they don't have any information on it and kind of grab that information so then they can start working towards it? And then looking at other technologies and seeing where it comes, like then contacting Hillphoenix, getting hold of us and seeing where we line up.
Yes, and that could be all over the place. You know, again, understanding what am I doing for my existing stores? What am I gonna do for my new stores? Where regulations are gonna go, and that may change all in itself.
Very
But
true.
we don't wanna go there, that's a different thing. But looking and focusing on CO2, if you're committed to doing a natural refrigerant and transitioning to a long-term goal of having it, whether it's for today's regulatory compliance, tomorrow's or next year's or whatever, you look at it from how do I provide the right solution to my company so that we have that long-term strategy? And that's how you look at adopting CO2.
Oh, that's a good start.
Great.
So if there's any questions on what we've covered so far, we did cover a good portion of it and it was a great information that flowed really well. So anything at all you want us to go back on, take another look at?
So I'm going to just transition here. Yeah. Get it. Just a couple of closing thoughts. You know, energy comparison, as we just talked about, will vary based on a lot of different things. So just understand the size of your store, the baseline and so forth, and make sure that it's an apple consideration for your condition, for your store. Then look at the right technology. And as we've stated, there are a lot of technologies out there that will help improve the efficiency of a CO2 system in any climate. And then also, we also have to look at it, and this another subject all in itself, CO2 has benefits, and how can we help do things with heat reclaim to improve the overall system of the store, including the HVAC system. And then also having that right information. You know, there's a lot of misinformation out there of what is benchmark, what is the right technology, where do I need to do it? Those things can be done, and a viable financial statement with an energy analysis can be put together for your application and your needs. And then you make the decision of what is the best move for my company for that long-term sustainability goal.